So you got a test on Monday. Any questions?
Not yet, but I'm sure I will.
Oh. Are you figuring you'll have questions on Friday, or figuring that you're about to come up with a question?
I will probably have some by Friday.
Okay. Anyone have a question at the moment?
How many questions is it?
Look at the old test. That's generally a good guide. I try not to write it too far in advance. Early on in my teaching, I would write tests in advance, and then some students figured out that, oh, if I asked them to come up with example problems concerning the test, the ones he comes up with usually are just like the ones on the test. And so I try to avoid that. Okay, let's pick up where we left off. So we have the three work energy relationships, the fact that the total work is equal to the change in kinetic energy. The non-conservative work is equal to the change in energy. And the conservative work is equal to the negative change in potential energy. So capital K is kinetic energy. Capital U is potential energy. We're about to do the unison thing, so get ready. What's the formula for kinetic energy? I'll give you a moment to check your notes. I will ask again in about 15 seconds.
1/2 mv squared.
That's, for those who missed it, there it is.
What did you say?
1/2 mv squared.
All right, here we go, in unison. What's the formula for kinetic energy?
1/2 mv squared.
That was lackluster. This time with feeling. What's the formula for kinetic energy?
1/2 mv squared.
I'm still hoping for more than that for enthusiasm. Now, potential energy, we've talked about conservative forces. There's a C there. And we have weight is a conservative force. Generalized gravitation. Generalized. Gravitational force is conservative. Then there's the ideal spring / the elastic. I think those are the only three I wrote down. I guess at some point the electric force. Every conservative force has a potential energy formula. So if I ask what's the formula for potential energy, the correct response is which one? What's the formula for potential energy? Wow. Good morning. Perhaps a little less muffled. Let's try that again. If I ask what's the formula for potential energy, the correct response is which one? So, what's the formula for potential energy?
Which one?
Better than the last time. So I'm going to give you these three. We'll derive this one right here. So the generalized gravitational formula is negative dig G, mass 1, mass 2 over R. The ideal spring or elastic spring is 1/2 lowercase k delta x squared. An electric force, case of E, Q1, Q2 over R. The electric force is something that will hit near the end of the semester. The ideal spring will get before that, probably, let's say early April, wrong semester. Sometime mid-November probably. This one we will get in chapter 9, I think it is. Wait, let's deal with that now. So I'm gonna take it. So I've got ground right here. I have an object that is going to fall. It's going to fall from this distance right there. Some distance h. I don't know what I'm going to do this. We'll do this. This is some initial height, and this is some final height. So it's going to fall this distance, and so we can go for the typical stunning visual effects. It's going to fall that distance. Force diagram. What are all the forces acting on this object as it's falling?
Force due to gravity.
All right. What else? Roll the checklist. So force due to gravity, that's the weight. Any normal force? Why not? Okay, that's required touching. Other? Why not?
There is no force to push it.
The force that I what?
Force to push the what?
That it, sorry. One more time.
Other means there is a force from outside.
Oh, okay.
There is no.
And I didn't mention it. All right, so that's gone. Tension? Why not?
There is no.
Friction?
There is no touch.
And we ignore air resistance. All right, so I have only one force acting on it. Is this a conservative force or a non-conservative force?
Conservative.
Yes, there we go. All right, so I know that the conservative work is equal to the negative change in potential energy. It's one of the work energy relationships. We sort of derived it last time. Conservative work is just conservative force times displacement. And change is always final minus initial, so it's the negative of u final minus u initial. So the conservative force is the weight downwards. The displacement is downwards. And so my conservative force is just the weight. Since the force and the displacement are in the same direction, I'm just going to multiply them. They're parallel. Weight times h initial minus h final. And it's h initial minus h final because I'm looking for a positive distance here. So that's equal to negative, distributing the minus sign, negative U final plus U initial. What is the formula for weight?
M times G.
So mg times H initial minus H final, which is mgh initial minus mgh final equals U initial minus U final. So the work energy relationship gives us this. So therefore, what is a formula we could use for U that would make this work? What do you mean? All right, let's try this slightly different tack. If I have x minus y is equal to 3 minus 2, what is a value for x and y that would make this work? Yes, okay. Now I'm over here. What would be a formula for U that would make this work?
Yeah, oh, that's, okay, that is what I was saying. MGHI minus MPHF?
That would be UI minus UF, but I want just U. What formula can I use for U that would make it work?
MGH.
There we go. What is another formula for U that would make this work? All right, before people answer that one, give you a slight chance to think. So if U is mgh, then U initial would be mgh initial. Because the mass and the acceleration due to gravity are not changing, we're assuming this thing is not bursting into flames on the way down. And it's not falling a great enough distance for G to change significantly. So U final is mgh final. Therefore, if I did U initial minus U final, that would give me mgh initial minus mgh final, hey, which is what we have right there. So if this is the formula for potential energy, we get this. So now back to what is another formula that we could do? It looks similar to this, but it's not quite this. What's another formula we could use that would still work? Go back over here. So Manal, I believe, suggested 3 and 2. What's another value for x and y that would also work?
Negative 2 and 3? Or plus 3?
Wow, was not expecting this amount of silence here. X minus y equals 3 minus 2. All I'm asking for are two numbers here, such that if I plugged in for x and plugged in some value in for y, I would get this. So I do 0 minus 1, I get,
Wait, no, not minus. 1 minus 0.
okay, so 1 and 0 also work. Let's get one more.
5 and 4.
So we have more than one combination that will get us this. What could we do to this to get the exact same difference?
Force times displacement, is that also the one?
No, not going that route. All right, so we had 3 and 2 to start out with, because it matches 3 and 2, makes sense. What's the difference here? And here? Is it coincidence that it's the same? Could that have a difference of 2 and this have a difference of 3 and it still work?
No.
Okay. What about from here to here? Could we make some general rule about the value of x and y so that this is always going to be true? Spoilers, because this is ultimately a minor point. I could just add 2. So this becomes plus 2 plus 2. So when I subtract, the 2's will cancel out, and I get back to the same thing. I can add 3 to both. And I still get the difference is that. I can add any number to the end here, and the difference between them is whatever that constant is, that's just going to cancel out. Because then I have mg, do it with the 3, mgh initial plus 3 minus mgh final plus 3. So I get mgh initial plus 3 minus mgh final minus 3, distributed the minus sign. The 3's cancel out, and I'm left with, again, mgh initial minus mgh final. The point is, all the work energy stuff tells us is the change in potential energy, not the actual value of potential energy. Because I can always tack on any number. Suppose instead, I have the ground here, but I want to make the height from this point right here. Make that H initial, and make that H final. Does my change in potential energy change? In other words, if this initially were, let's say, 5 meters and 2 meters, and then I said, you know what, let's just add an extra 2 meters to each, so let's make that 7 meters and 4 meters. Does my change in height change?
Yes.
Is that a yes?
Yeah.
To what?
Well, you would add 2 to each, so, I guess the final, I don't know.
All right, so given that these numbers here, initially, H initial minus H final was 5 minus 2. And then I said, let's have a new reference point. Let's just figure out a height based upon this place 2 meters below the ground, the surface of the ground. So now it's 7 minus 4. Did we change? Did the change change?
No.
So ultimately, when you're talking about height, the fact that we can do this, we can make the height based upon anywhere we want, whenever it's convenient. Now, most people make the height relative to the ground. But you don't have to. Let's actually use this. So MGH, and then to any of these, you can always just add a constant. Plus some constant, plus some constant. Let's see, let's do something nice here. So let's make this a 3, 4, 5 triangle. Actually, before we do that one, we'll come back to that. Let's actually do numbers here. So I have a 5 kilogram mass that starts out 20 meters above the ground. It is going to fall 15 meters. So this is 15 meters. So it'll end up 5 meters above the ground. And I want to know how fast is it going at this point. So I take it and I drop it. So I'm going to drop. How fast is it going when it gets to this spot right here? Now we could use the chapter 3 stuff, but what I'm hoping to do is introduce you to energy stuff. So as it is falling, what are all the forces acting on it? And considering how quiet people are, definitely need this closed. So as it's falling, what are all the forces acting on it?
Just wait.
All right, conservative or non-conservative? So if I start with the second equation over there, the second work-energy relationship, we have non-conservative work is equal to the change in energy. The only force acting on it is conservative, so the non-conservative work has to be 0 because there's no non-conservative force. That's equal to E final minus E initial. In other words, because only conservative force is acting here, we have only conservative work. In other words, my initial energy is equal to my final energy. Energy is conserved if the only thing doing work are conservative forces. Thus the clever name, conservative, conserves energy. We are assuming that this is not bursting into flames all the way down. There's no sudden annihilation and burst into a beam of light. In other words, we're only dealing with mechanical energy here. And I have two types. There's kinetic plus potential. So the sum initial is equal to the sum final. Here we go again. It's even, was written on the board. What's the formula for kinetic energy?
One half mv squared.
We're doing this in rounds. It's like a wave. All right. I want to hear everyone's voice. You know what the answer is, so I'm just going to point to you, and I just want you to say it in a nice, loud voice.
1/2 mv squared. 1/2 mv squared. 1/2 mv squared.
1/2 mv squared.
1/2 mv squared.
Half MV.
Go.
Half
Go.
MV.
1/2 mv squared.
1/2 mv squared.
1/2 1/2 mv squared.
Yay, all right, heard everyone's voice, thank you. All right, so the formula, 1/2 mv squared, 1/2 mv, its initial squared, plus, what's the formula for potential energy? Thank you, the one associated with weight.
MGH.
1/2 mv final squared plus mgh final. All right. Now let's get rid of stuff. Is any of this stuff equal to 0? We'll go step by step here. Is 1/2 equal to 0? Is the mass of the object 0? Did somebody say yeah? Okay. Is the initial speed 0?
Yes.
What's the key word? Why do you know it's equal to 0?
Because it hasn't been dropped yet.
We need to take it into account as after I've let go. But when I let go of it, the fact that it's being dropped, at that very brief moment, as soon as I let go, the speed is 0, or close enough. So that's 0. Is the acceleration due to gravity 0?
No.
If the acceleration due to gravity were 0, what would this thing do when you let go?
Well,
Yeah. Is the initial height 0?
no.
Okay. Is the final speed 0? Final speed being the speed at this point right here. That was a no?
Yes.
Yes, that was a no?
No, yes, that was this is your, I don't know who said no, but I'm saying yes, it is here.
It is 0 when it gets to here?
Yeah.
Why?
So it stops right there. And then it goes.
Why does it stop there?
But that's not considered the ground,
No,
right?
ground, this is the ground down here.
Okay.
This is just some spot 5 meters above the ground. I feel very confident if I took a ball to the top of a 2-story building and dropped it, when it's about 5 meters from the ground, it's not gonna suddenly just stop. Again, it'd be a really cool effect if it did, but no, this final speed is not 0 here.
You just want the speed of when it is there.
Yes,
Okay.
yes. And then final height, is the final height 0?
No.
Okay. Where is height equal to 0?
On the ground.
You're asking?
No, that's
You're
on the
saying-
ground.
Why is the height equal to 0 here?
Because it's ground level?
Nope.
Would it be depending on where you start?
Nope. You forget the power that Manal has. And I say Manal just because I heard her first. It could have been any of you. Why is height equal to 0 at the ground? Because Manal said so.
Oh, yeah, that's what I meant.
You set height equal to 0 wherever you want. It's not gonna change the answer. So we'll start it out here, then we'll put it in a different spot. Okay. So now, mathematically, every term has mass in it. We could cancel mass out and save us just a little bit of time. Not every student is comfortable with that. So you want to cancel mass out or leave it in? What was that, Carrie? I heard you first.
Leave it in, why not?
Take it out?
Leave it in.
Leave it in? All right. So we have 5 times 9.8 times initial height of 20 equals 1/2 times 9.8 times V, that's what we're trying to find, VF squared, plus 5. Oops, that should be a 5 there, not a 9.8, that should be a 5. Plus 5 times 9.8 times 5. Because, dang it. I don't like using the same number twice, but this is 5 kilograms here, and this is 5 meters here. So let's do the math. This would be 980. So conveniently chose numbers that would work nicely. So I have 980 equals 1/2 times 5 is 2.5. So 2.5 V squared, V final squared, plus this, $245. Okay. So how do we solve for VF?
Set everything equal to VF. Or
How do we got it step by step.
When you subtract both sides by 245,
Yes. We're trying to isolate it, so you start peeling away the layers of the onion there. Minus 245, minus 245.
and then divide by 2.5.
That will be the next step. So so on the right hand side we have 2.5 VF squared. And on the left side, so that would be 3, 5, 735, I believe. And then, as Taylor said, divide by 2.5. So on the right hand side I have VF squared, and on the right hand side I've got something
294. 294.
294. And then what?
Take the square root of both sides.
Yep. We're undoing it. So the opposite of squaring is square root. So I get VF is the square root of 294. Was it 294 exactly?
Yes.
Okay. And because we're living in post 70s, I assume you have a calculator. 17.15. That's a decimal point there. So we did all that work, and we're missing something.
meters per second?
It would be. There we go. So if I drop this thing, it would be going 17.15 meters per second. Let's change. All right, questions on this before we're going to change where h is equal to 0. All right, so let us make, instead of that, let's make h is equal to 0 here. At the finish line. So now, this term is going to drop out. Because the final height's 0, because, well, that's because I said so. And so we're left with mgh initial is equal to 1/2 mv final squared. So that's 5 times 9.8 times, what's the initial height now? Not 20 meters.
15.
Yeah, it's based on, since 0 is now here, it's 15 meters above that. So 15, it's really not much better, is 1/2 times 5 times VF squared. So on the right-hand side, I got 2.5 VF squared, and on the left-hand side, I suspect we're gonna get, how does 735 sound?
That's all right.
Because that's what we had right there. And at that point, it's just the same. So we get the same answer. So now, we're gonna do it one more time. We'll get the same answer. But I do need to point out one thing here. Questions before I change where height is equal to 0? Get rid of that. Let's make h is equal to 0 at the top. So now my initial height drops out. Final height is back in. And so now we have, and I guess I need to erase my triangle there. Zero on the left-hand side because it starts out at height is equal to 0. It starts out at 0 speed, so we have 0 on the left-hand side is equal to mgh final plus 1/2 mv final squared. So I have 0 is equal to 5 kilograms times 9.8 meters per second squared times, what is my final height?
-15.
Yes. Suppose when we're dealing with vectors, we decide what the positive direction is. Suppose we said down is positive. What would the final height be?
+15. +15.
No. It would still be -15. Because we're not dealing with a vector here. It is built into the system that when you go in the direction of the gravitational force, that you're going to a lower number. So it's still going to be -15. Is equal to, oops, sorry, no, plus 2.5 VF squared. So this right here, so we have 0 is equal to -735 plus 2.5 VF squared. When you add 735 to both sides, you end up back here and you get the same answer. Oh, let's solve it one more way. Just because you can feel the excitement of wanting to do it. Questions before we solve it a different way?
I see why we put it equal to 0 when the height started over there, but are we putting it equal to 0 because that's your initial point of starting?
Typically, when you're trying to establish where 0 is, the usual places are at the beginning of the problem or the end of the problem. Just so that a term drops out, it's a little bit less math to do. Because the first time we did it, we had h is equal to 0 at the ground, we had 3 different terms. But if you set h is equal to 0 here, we have only 2, or h is equal to 0 here, we have only 2. So so traditionally. Most people are comfortable with the lower point being h is equal to 0. But it doesn't matter. And then some people will always stick with the ground because that's what works for them. And that's fine. Did I answer your question? Or address it at least?
Yeah, I get it.
Okay. All right, let's do it the chapter 3 way. So there's a formula that Q had in chapter 3 where if you take an object and you just drop it, of how far it's gonna go, it was that the displacement is 1/2 GT squared. I guess he had distance is 1/2 GT squared. It's just going in one direction. So in this case, it's gonna drop 15 meters, and that's gonna be equal to 1/2 times 9.8 times time squared. So we're just gonna figure out how long it takes for it to actually fall that distance. So this is 15 is equal to 4.9 t squared. Same process as we had over there, we're gonna divide by 4.9. And so t squared is equal to whatever, something a little bit more than 3.
3.06.
3.06, okay. And so time would be the square root of that. So 1.72.
1.75.
1.75, all right. Units?
Second?
Yes. Now that doesn't tell us how fast it's going, that just tells us how long it took to fall. But also he talks about how fast is it going. Well, the speed is just going to be GT. So the rate at which speed changes times how long it's changing. So this would be 9.8 times 1.75. And my gut tells me it's going to be somewhere around 17.15. Meters per second. Shocking, it's the exact same answer. So we just went through a whole bunch of stuff here to come out with basically what we could have done in chapter 3. However, we have a little bit more power here. So I'm about to do the ski problem. Any questions before I erase this? I'm gonna, I guess. I'm gonna do that. No, I'm gonna skip the 3, 4, 5 triangle. Sorry about people put that down. We'll go straight to the ski problem. Any questions before we do the ski problem? Do recognize when we have h is equal to 0 at here or here, it starts out with all this potential energy, no kinetic. Kinetic 0, potential is whatever that value was. As it falls, the energy is being slowly transferred between the two objects, between the two energies. So it's going from potential into kinetic. In this case, there's no potential at the end. In this case, when h is equal to 0 here, there was still some potential. But in either case, the same amount of potential energy got turned into kinetic energy. The whole idea of conservation is that you don't lose it, it just changes from one form to another. All right, the ski problem. It's supposed to be a skier. Starting out 50 meters above the bottom down there. And ultimately, the question is, how fast is the skier going down at the bottom? That's what we're trying to get. A little bit more information here. The initial is practically 0 meters per second. If you need to, he is delicately balanced at the top in an unstable equilibrium, but he is in equilibrium. A gnat lands on his back, which is just enough force to get him to start moving, and then he starts going. We're making it frictionless. Now, to figure out about the energy bit, we do need to do a force diagram. And the force diagram is going to basically change a little bit as he's going down. So what I'm going to do is I'm just going to take a specific point at this point right here. When he's right there, let's do the force diagram on it. So let's sort of need to draw. All right. So what are the forces? Let's put up our. What are the forces acting on him when he is right there?
Friction.
Frictionless.
Weight.
Acting which way?
Down.
Okay.
Normal,
Acting which way?
parallel to the slope. Parallel to the slope.
No.
Or wait.
The
Oh
other
no,
one.
sorry. Perpendicular to his skis and the ground. Yeah.
All right, so there's normal, weight, other. Nothing was introduced. Tension, all right, gone. And friction we've already eliminated. If this were just a plain old force diagram problem, yes, friction definitely would be included, but I eliminated it just to make it solvable. All right, so I have two forces here. So let's take them bit by bit. This weight, is this conservative or not conservative? I should probably say non-conservative. Yep, all right. Normal force, conservative or non-conservative? All right, so we now have a non-conservative force involved. Now let's think about the work. Work is force times displacement. Remember that dot products, like parallel, they hate perpendicular. So at this moment right here, when he is traveling this way, so this is the direction of his velocity at that moment, and then the normal force is this way. What's the angle between them? Yeah, it's a right angle. So what is the dot product between, I guess, instantaneous displacement? So instantaneous. What is the dot product between the normal force and the instantaneous displacement? Since they're perpendicular. Right, overthinking it, and I missed.
The result of the forces, the two forces.
If they're parallel, yes, but they're perpendicular here.
Would it be like y squared plus the,
No. You think of doing a Pythagorean theorem? All right, when you're doing dot product, the question is how much of one vector is in the direction of another? How much of the normal force is in the direction of movement at this instant? How much of this is in the direction of none? So the dot product is 0. The normal force does not do any work at all. There's no movement in the direction of the normal force. Matter of fact, no matter where he is, the normal force direction will change, but it is still perpendicular to the movement. So the work, the non-conservative work, is 0 joules. Because the normal force is perpendicular to the instantaneous displacement. The only thing doing any work is the weight, which is conservative, and we are back where we were before. Energy is conserved. I'm going to write up the first couple of steps. This is look very similar to what we did with the object falling. Matter of fact, it's still in white. We have weight non-conservative is equal to the change in energy. The non-conservative work, last time it was 0 because there was no non-conservative force. This time it's 0 because the non-conservative force is perpendicular to movement. Equals E final minus E initial. E initial equals E final. K initial plus U initial equals K final plus U final. All of that just like before. And one more time with feeling. What's the formula for kinetic energy?
1/2 mv squared.
A little better. 1/2 mv initial squared plus, what's the formula for potential energy in this case?
Which one?
In this case.
Oh.
No, I do appreciate that.
MGH.
Yes. Why is it MGH? Why does that apply to this one? Because I wrote up 4 different potential energy formulas. There's more than those 4, but I wrote up 4 of them. Why is MGH the one associated with this one?
Because there's weight.
Yes. So this is the exact same as we did before, up to here. Now potentially it might change. What can we get rid of? What is equal to 0?
Initial velocity.
Or speed. But, yep, that's 0. Because VI is approximately equal to 0 meters per second. It's written over there. What else is equal to 0? If anything. We'll revisit that in a moment. Where do you want to make height equal to 0?
The ground.
Down here? So, back to this. Anything else equal to 0? And why? So we now have, we are left with mgh initial is equal to 1/2 mv final squared. And now if you're given a problem like this, I didn't tell you his mass because ultimately the mass does not matter. So if you're given a problem like this and you're not given the mass and you have mass in a formula, one of two things it means I made a mistake and I meant to give you the mass, or 2, the mass doesn't matter. In this case, it doesn't matter. So if you're faced with that, you can either try to figure out, all right, how can I get rid of mass, or just make up a number that's not 0. So do you want to get rid of mass or just make up a number?
Get rid of it.
All right, so we'll divide both sides by the mass. Mass cancels out, mass cancels out. So I'm left with G, H, initial, is equal to 1/2 VF squared. All right, let's assume it takes place on Earth. So 9.8 meters per second squared. Times the initial height, which is 1/2 times VF squared. That's what we're trying to find. So this is 490 equals 1/2 VF squared. Multiply both sides by 2. So I have 980 is equal to VF squared. So VF is the square root of 980, which is 31.3.
Is that 2 divided by 490?
Wait, where are you?
Right there, where your marker is. Oh, yeah. What does that first part say?
That basically, this is what we had, and I said just multiply both sides by 2.
Okay.
Is that random?
It'll cancel out the 1/2.
Yeah, that's. You could divide by 1/2, but dividing by a fraction is the same as multiplying by the reciprocal, so dividing by 1/2 is the same as multiplying by 2. Square root of 980,
31.3.
31.3. Oh. Units. Questions?
So in this case, are you saying that the normal force is 0?
No, I'm saying the normal force doesn't do any work.
Okay, so it's just like not affecting the problem?
Not affecting the energy transfer.
Okay.
I mean, normal force is affecting the problem, otherwise he'd be going through the snow. But it's not affecting the energy. So once again, we start out with all this potential. We start out with 490 joules of energy and no kinetic. And then as it goes down the ramp, all that gets transferred into kinetic. And so we have all kinetic at the end, no potential energy. Unless you want to change the height to where height is equal to 0, then we can give them some potential energy. But it's still the same amount of potential gets transferred over into kinetic. All right. So he gets down to the bottom, he enjoys it, he goes back up to the top. What he does not realize is that while he was making his way back up to the top, there was a cave-in. And he doesn't realize it until it's too late. So he goes skiing down, and now, for those of you concerned with the stick figure safety, at the bottom of this cave-in are kittens, clouds, and cotton balls. He landed safely. No kittens were harmed. But of course, if there'd been cats down there, he could have landed on them and who would have cared? But no kittens were harmed. I forget, I think I probably asked this. Who are the cat people in the class?
Nice.
All right. Right before he hits the kittens, not the kittens, sorry about that, the cotton balls and clouds, how fast is he going? . How would you solve it?
The same way.
Okay, so where does it change? So while he's on the slope, the normal force still doesn't do any work. Once he's in the air, there is no normal force. So we're still here. That's still true. Is this still true? That energy is just kinetic plus potential? Assuming it's not bursting into flames.
Yes.
Okay. Kinetic energy is still 1/2 mv squared? There was a couple knots, okay. Potential energy in this problem still mgh?
Yes.
All right, so that still holds. You still want to make height is equal to 0 at the bottom? I think I heard a uh-huh. All right, so that goes away, that goes away. So we're here now. The mass still cancels out. G is still 9.8, the initial height is still 50. How fast is he going just before he hits? So, yeah. It's the same problem from an energy point of view. Now, what is different is the velocity. The velocities are not the same, but the speed is. And this is the power of of dealing with energy. But we do lose some information about direction. So when direction matters, you, for the most part, don't look at it from an energy point of view. All right, so speed is still the same. Questions before he makes his way back up to the top? All right, so the kid is showing him the secret door, and there's some stairs inside the mountain here, which lead him back up to the top. I guess the way I've drawn it, he has to do some climbing. So you want to take it to, I'll take it to there. While he's going his way back up, there's a snowstorm, especially in this localized area, and it fills back in. The kittens are safely inside. And the owners of the ski resort decide to put a giant spring at the bottom. You know, the way ski resort owners do. Now we do need to have a piece of information over here. I have to tell you the spring constant. So when I put up the formula before of 1/2 k delta x squared, this k right here is known as the spring constant. And what k tells us is how much force is required to stretch the spring or compress a spring 1 meter. Now, when we get to that section in chapter 19, somewhere around there, we'll be able to do something better than what I'm about to do. Right now, I'm just going to tell you. So let's make this 40 newtons per meter. And that tells us that it takes 40 newtons to stretch it 1 meter. So how many newtons does it take to stretch it 2 meters?
80.
And 3 meters?
1.
Yeah, and so on. I also have to give him a mass. So let's give him a mass of 70 kilograms, which is, I think, somewhere around adult average. It's an ideal spring here, so any force that it exerts is a conservative force, so energy is still conserved. Normal force is still not doing any work because it's a lazy bum. Or my oldest first cousin's first husband. So kinetic energy, sorry to spoil it for you, I know you really wanted to say it again. Now recognize we have two conservative forces involved in the problem. We have the weight of the object, and we have the force from the spring, because he's going to run into it. And so I have two potential energy formulas. I still have mgh, but I also have the 1/2 k delta x squared. I guess I never really defined delta x, because delta x is amount, spring, compresses, / stretches. In an ideal spring, if it takes 40 newtons to stretch it 1 meter, it takes 40 newtons to compress it 1 meter. The spring is not going to interfere with itself. You know, like a slinky, if I drop the slinky will eventually collapse into itself. There's only so far it can go. Ideal doesn't do that. So what I want to know is how much will the spring compress, and so this delta x that's what we're trying to find. That's the initial. It's equal to 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. And now the part where we make it simpler. What can we get rid of? What is equal to 0? Besides, well, I guess I didn't bother erasing that, so that's gone. Final H, you said? Why?
Because it's, you said so.
Okay. I erased the H is equal to 0 there, so we could have changed it. H is equal to 0 at the ground, because whoever wants to take credit. Yes, I think I heard Cheyenne say it the first time, so I was giving Cheyenne credit. Or we, if we want to do it as a collective. All right, so that's 0. What else can we get rid of? There's actually 2 more things we can get rid of.
Mass?
Now, we actually cannot, because this term does not have mass in it.
Okay.
1/2 k, initial square.
This, yep. Because nothing's hit the spring's just sitting there. As a former colleague once said, sitting there fat, dumb, and happy. This is 0 because delta x, the initial, is 0. All right, got one more thing we can get rid of. No, not if h is equal to 0 here, the initial h is still 50 meters.
1/2 mv final square,
Why?
because you're not trying to find the final, you're trying to find 1/2 k.
All right, so we are trying to find that. You are right, that is 0, but let's see if we can come up with a better explanation. Why is this 0?
Because none of the other ones can cancel out.
Okay, process elimination. All right, we're trying to find how much the spring compresses. So suppose VF is not 0. What's happening to the spring? If he's still moving, what's happening to the spring?
He'll go through the spring.
No.
He won't stop.
The spring comes together.
Presses.
The spring will be 0 then.
Let me go grab a spring. We'll do the stretch instead of, all right, so so my hand will be, in this analogy, the spring at the bottom of the cliff, and then my hand is the skier. So if the velocity, or if the speed is not zero, what's happening to the spring? I think somebody said it.
Stretch.
Yeah, it's still stretching.
For why?
Why?
Yeah.
If speed is not zero, that means my hand is still moving. And my hand's attached to it. Or in this case, he's hitting the spring. He's not going to go through the spring. He's going to hit the spring. If he's still moving, that means the spring is still compressing. So when we get to maximum compression, he has to have stopped. Otherwise, that spring is still compressing. So we start out with all this gravitational potential energy, and we end up with all this elastic potential energy. But our formula has now been reduced to, I have mgh initial is equal to 1/2 k delta x final squared. And now it's plug and chug time. Or for those that like dealing with letters, come up with a formula for delta x and then plug and chug. But mass, 70. G, 9.8. Initial height, 50. Equals 1/2 times k, which is 40, times delta x final squared. So 50 times 9.8 times 70.
$34,300.
One more time.
34,300.
What are the units of this 34,300?
Meters per second?
No. We multiplied all that together. So we had kilograms times meters per second squared times meters.
Meters per second squared? Kilograms per second squared?
No.
Newtons.
No.
Right?
So we have a kilogram times a meter per second squared times a meter.
Meters squared? No.
Is that joules?
Yes, it is. Or, I think the way you were going, it's also a kilogram meter squared per second squared. You can stick anything over 1 to make it a fraction. You multiply the tops and you multiply the bottoms, so you get kilograms meter squared over second squared, which is just a joule. All right, so we have the math problem here. Let's divide by 20 because we're trying to isolate our variable here. So 1,715. So I have 1,715 equals delta x squared. Assuming I did my math right. And so this would be the square root of
41.
units.
Joules?
Not at this point.
Meters per second. Meters per second.
You went too far.
Meters per second squared.
It's not meters per second squared. What is delta x?
Newtons per meter. No.
Meter.
Just meters.
Just meters. When I said you went too far, if you just stopped after the word meter, meters. It's how far it compresses. So he comes all the way down the hill. He's going about 31 meters per second, hits the spring. Spring compresses a little over 41 meters. And then it's going to shoot him back. So now he's being shot backwards. How far up the hill is he going to go?
41.41 meters?
No. Think in terms of energy. So he has all this potential energy to start out with, gravitational potential. As he's going down the hill, it's all becoming kinetic. And then once he hits the spring, all that kinetic energy gets converted into our elastic potential energy. And so now, as he gets shot backwards, all that elastic potential energy from the fact that we have a coiled spring gets converted back into kinetic, which then gets converted back into gravitational potential. How far up is he going to go? Where's energy being lost or gained? Total energy.
When he hits the spring?
Except the hitting the spring exerts a conservative force, so energy is not lost there.
When it's fully compressed.
It's still a conservative force. No. And by the way, in reality, if he hit the spring, he would heat up some and some energy would get lost into sort of internal kinetic. But it's a nice ideal stick figure. Right? What non-conservative force is going to be taking energy out of the system? If we're losing energy, that means there's non-conservative work being done.
Normal?
Except normal is perpendicular to the movement, so it's not doing any work.
Is it after he leaves the spring?
So what non-conservative force is doing work on him?
You said weight was conservative, right?
It is.
Friction?
That's still frictionless.
Oh, that's
Okay.
right.
I didn't introduce any additional thing in the system. There is no loss. How far back does he go? Again, this is a nice ideal problem here. There's no friction. The skis don't grind into the mountain or anything like that. He actually will reverse it and come all the way back up here. And then that lands on his back again, and then he'll. Matter of fact, as he's coming on the, if he's traveling on the way back, and there at some point suddenly there's a small little breeze that hits him in the direction he's going. That would introduce just enough energy to make him go all the way over to the other side. But how fast is he going when he gets down to here? No, how fast? Yep. Meters per second. I hope you have a wonderful day. And I guess we got lab Friday, test Monday. Nothing but good times ahead.